Well, good morning. You don't have to stay if you don't want to. It's just the two of us, but I'm going to go through some things on capacity planning. So if you're interested, you can hang for a bit.
Okay, no problem, Professor.
All right. Okay. Just going to kind of do it this way. I'm not going to, I think, blow this thing up. Although, let me see if just for grins, it'll open that way. Yeah, that might work. Okay. All right. That should be a little bit better. All right. So, again, for today and Friday, I'm going to speak a little bit about capacity planning. And, we're getting near the end of the semester. So, next week, I think it's reading days. And so I think this week might be it. But let's talk a little bit about this and see what we can pick up. So, the idea of what we'd like to cover, today and then on Friday, finish up on Friday, is some of the elements of capacity planning and why they're important, how we use them, and so forth. So basically, it's kind of like so much else that we've done with OPPM, where we look at limits, upper limits, lower limits. We look at error and things like this. So capacity is kind of the upper limit or ceiling on the load that an operating unit can handle. So the upper limit would be whatever. If we look at the Betty's Bats example and we say, look, we have the capacity the way we laid it out with three different plants and 6 lines per plant and 3 shifts per day and so forth. We came up with excess capacity. We came up with almost 1.3 million bats, if I remember correctly. And when we did the forecasting, our actual forecast was 900, whatever it was, a little bit less than 950,000. So we have excess capacity, but we know what the capacity limit of this mythical Betty's Bats operation would be, something approaching 1.3 million bats. But it takes into account a lot of different things. So, for example, when we start to incorporate other things that come from some other courses, but MTBF, mean time between failures, we start to see that, well, we're looking at things as if machines never break down, as if there's no scrap rate. And we talk about error and we talk about the kinds of things we'd want to do to control error. But in reality, we need some amount of excess capacity. So capacity for our purposes includes the idea of equipment and space and employee skills and so forth. The basic questions in capacity are, well, what kind of capacity is needed? How much is needed? And when is it needed? And those seem pretty intuitive things. So the importance of capacity decisions, well, it impacts the ability to meet future demands. So if, for example, we had max capacity in the Betty's Bats example, we would be sitting back saying, okay, well, the business can't grow. And obviously, continuous growth is something that every business kind of seeks because it's the idea of stay small, stay large, but in between you get crushed. So you have to almost constantly grow. Capacity decisions affect operating costs. They're a major determinant of initial costs, and they obviously involve the long term commitment, both of capital resources and financial resources, to be able to do other things. They affect our competitiveness or competitive advantage. They affect the ease of management. And then the obvious things like globalization and so called long range planning and so forth. So, when we talk about capacity, we talk about it in a couple of different ways. We talk about design capacity for one, and that's the maximum output rate or service capacity an operation, process, or facility is designed for. So the maximum output rate of Betty's Bats, for example, is actually the idea that we can produce almost 1 million bats per year. Now, in reality, that's based on everything running smoothly and so on and so forth. But the maximum output rate, if we broke it down, if we look at the production sheet, we came up with different sheets with different numbers talking about throughput and bottlenecks. So, in reality, it might not be as simple as just having three production lines or six production lines or however many, because we'd be looking at bottlenecks and we'd say that, okay, so the longest single operation is really where the bottleneck is. So we need a few more of those machines, for example. So we don't have to have an entire production line. We just have to have more of a parallel network at some point. So design capacity. Um, Effective capacity, well, design capacity minus whatever allowances, personal time, maintenance, downtime, scrap rates, and things like this, which delivers an actual output. And the rate of output that we actually deliver, and again, this is, with Betty's bats, it's hard to look at that because we just sit back and we do some arithmetic and we say, well, okay, so we forecast this, this is what we have to produce. And the actual output rate might be different based on things like mean time between failures, known scrap rates, and so on and so forth. So efficiency, we talk a lot about that. We talk about efficiency and optimization and so forth. And so efficiency and utilization, well, efficiency is the actual output, what we actually deliver over what is in effect our capacity or arguably effective capacity. The utilization or utilization rate is actual output divided by design capacity. And both of these we look at in terms of percentages, just makes it easier to say, well, we're not 100% efficient, but we are, whatever that number might be. And this is where, excuse me, some of the things like personal Kaizen and individual Kaizen come into play because we're always trying to improve processes, improve operations, et cetera, all towards the end of greater efficiency. In other words, getting that percentage number higher. And then the utility of what we do, the utilization rates of different things, and so forth. Efficiency utilization example, textbook example, design capacity. Well, we can do or deliver or handle 50 trucks per day. Now, the effective capacity is 40 trucks per day, but the actual output is actually 36 units per day. So again, we look at these measurements and we say, okay, so in terms of efficiency, we're running at about 90%. In terms of utility or utilization, we're looking at 72%. An interesting example, which probably would not thrill everyone, is when we, currently, and it wasn't always, this way. I mean, COVID had an impact, actually had a very big impact. But when we started the School of Business down there, we had to fight to get classrooms because the classrooms were packed. The professors wanted classrooms with higher technology and so forth. So, I mean, the place was packed after COVID, and once the notion that well, we can work from home and do these things online and so forth. Well, so when you talk about utilization, if you look at the classrooms and you look at the square footage of the School of Business, the utilization rate has to be way down, which has to be concerning to leaders and managers, in quotes, of the firm, because again, when you've got a very low utilization rate, you're paying an awful lot of money for that space. So that would be another example. Excuse me. Um, some of the determinants of effective capacity, well, facilities, the design and layout. And we talked a little bit about, the Betty's Bats thing. We looked up on the sheet and we said, okay, we've got these operations. We looked at Frank's Fine Floats and it was whatever, A through H or something like that. And then we had a few less with Betty's Bats. But it was the idea that we would bring in a raw product. The first operation was a slugging operation. So we said we took these big aluminum bars and we cut them into bite-sized pieces. And then we had a first extrusion and a second extrusion because you couldn't move metal to where we needed it to move without total destruction in one operation. So we had to have two. And some people call it swedging and so forth. But, in any event, so we had two operations there. And the point being that, that was not a layout that was designed for maximum efficiency. And part of it is because we had production lines, but again, the throughput was based on the longest single operation. And we might have been able to improve that by putting a second machine in parallel to that so that there were no slowdowns or bottlenecks, and so forth. In other words, each operation was roughly similar. And then rather than just having a total, minute per piece added for all the handlings, actually measure the handlings and look at that in terms of automation and what the effective output would be and so forth. So facilities design and layout is obviously product and service factors. Well, product design and product mix. Excuse me. There are several ways to make an aluminum baseball bat. And some would argue that, well, instead of taking a slug, a solid piece of aluminum, a chunk of aluminum, and then putting it into an extruder and just using a positive and negative in effect, positive and negative cavities, like a die type operation, instead of doing that and forcing so much metal around it and all of this stuff and then having to do it a second time, would it not, rhetorical question, of course, be easier to take an aluminum bat, which ultimately is hollow anyway, take an aluminum bat and just take, basically aluminum tubing instead of aluminum bars. And instead of having slugging and swedging operations, take these bars, feed them in, and instead of extruding them, these big extrusions, actually swedge it's called a swedging operation where you kind of, as you're rolling the bar, you crimp down on the small end. You take the fat end and you make it smaller. So a swedging operation versus extruding operations. And that might change things like the way we design the product and so forth. And it might lead us to other opportunities in terms of product mix and so forth. And some of the process factors, well, we talk about quantity capacity and quality capacity. Being softer in terms of the force, so it takes tremendous force to extrude something. You're taking something solid, you're forcing it into a positive and negative mold, and it's almost like if you were to take a bowl, stick some Play-Doh or dough that you were going to make bread out of or something like this, and then drive your fist into it, and what happens? Well, the dough rides around your fist and it kind of squeezes its way around the sides of the bowl. Well, that's in effect what you're doing with the extrusion. Only with metal, obviously, it takes a lot more force and so forth. So again, when we look at process factors and everything, we might improve quality by disturbing and moving metal less, and that would be a swedging operation versus an extruding series of operations. And that might also impact because the throughput with that might be actually quicker. So we might improve in terms of quantity, we might improve that as well. Human factors, well, job content, job design, training, and experience. I've maintained to pretty much every class I've ever had that the repository of the knowledge of the firm lies with our human resources. So again, the idea of why something is designed in a particular fashion, why we set the floor, the layout up this way versus that way. These are all human inputs based on experiences. And, it's kind of the idea that, well, we've done it this way, we've always done it this way. And instead of saying, so we're always going to do it that way, we know at least where the bones are buried. So we know why it was done this way. So we don't have to repeat and relearn the same things over and over and over again. That is, unless we have high turnover rates and these human factors march out the door and so forth. So then, we spend some great inefficiencies, great inefficient time relearning things again and again and again. Policy factors, I won't speak to. That's more the strategy course and so forth. But it's obvious that in terms of operations policy and business policy and risk policy and other things that we have, there has to be a congruence. We have to all be singing off the same page, and I'll leave that one where it is. Operational factors, well, scheduling here again, When we looked at Betty's bats, we said, well, one plant's not enough. And we said one shift wasn't enough. And even when we did three shifts in one plant, it wasn't enough. But if we put more than one production line in the plant and ran it three shifts, well, that made a dent. And then we just had to add two more of those same facilities to give us basically three facilities, these multiple production lines, three shifts a day, and so forth. And that gave us excess capacity, but the ability to deliver on the capacity we were required to meet by virtue of our forecasts. Supply chain factors always impact what we do and don't do. It's kind of like an external mean time between failures. If we run this production facility with very limited excess capacity and one of the machines goes down, we're in trouble. It's like running a busing operation that you rely on 100 different, let's say, school buses, and all of a sudden three of them broke down. Well, if you don't have excess capacity or sufficient excess capacity, then you've got a problem and you can't meet the mission, so on and so forth. Well, same kind of thing here. These operational factors, that we're talking about specifically here are things like where we see, maintenance and breakdown. This is that mean time between failures because machines don't operate 100% of the time. Scheduling is the same thing. What about if materials under a theory of just in time delivery just don't arrive in time? And we say, okay, well, these supply chain factors that influence our operational factors and so forth are congruent, or they're supposed to be congruent. That was the whole idea behind establishing a preferred supply chain, tier one suppliers, and so forth. And what happens when that doesn't happen? And the greatest recent example of that was COVID. Arguably the nation, the government, whatever, needed ventilators and, had all kinds of contracts for delivery of ventilators. And the tier one suppliers couldn't supply it, because their supply chain broke down. Now we established our supply chain with them so that we didn't have to go deeper than our tier one supplier. It was their responsibility to make sure the other supply chain elements on their end, in other words, further down the food chain, if you want to look at it that way, that they were up to snuff and that they had backup resources and plan B and so on and so forth. And that obviously didn't happen. So supply chain factors are a big issue. And other external factors, we look at environmental issues when we talk about SAP ETOP. And the environmental side are things like, political, legal, regulatory, economic, so on and so forth. And so this is where we see standards, regulations, unions come into play, how many hours and what kind of work, pollution, safety, blah, 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 blah. So all of that is a factor in what we, try to do and try to deliver. Strategy piece is pretty straightforward. Capacity strategy for long-term demand patterns. It involves having a growth rate to start with and then realizing what that growth rate is. So when we look at Betty's bats, all right, and they were just ridiculous numbers, of course. And, at one point, it started with whatever it was, 750,000 bats. And next year it went up from there and then it hit 1 million bats. And so if those three elements were all we looked at, we would sit back and say, okay, so our firm, the demand for our products is growing exponentially, and would be able to identify what that was. But then we also saw a reversal and it went back down from 1 million bats, which tells us that, look, it's not a straight line. Things in life are probably more curvilinear than linear. And that's a great example of that. So, we have this noise that we have to attenuate and try and define and decide some underlying trend line. And we did have a technique for doing that. The linear regression or linear trend line gave us a linear projection, potentially of growth. And that's something we'd be interested in because what we're trying to do is attenuate this variability, this uncertainty, of demand clearly, and be able to respond to that. Once we have a growth rate, we can make decisions regarding capital commitments, employee retention, automation, so on and so forth. And not the least of which is to look at and say, hey, look, with this kind of a growth rate, while we're trying to produce something on the order of 950,000 bats, this year, we have an aggregate capacity based on 100% efficiency, which is not going to happen, but we have an aggregate capacity of something like 1.3 million bats. Well, depending on the growth rate, that tells us how long we have before we have to make some other decisions, or do we need to be making other decisions, at time of the instant, now. And then the factors that come into play, obviously, are the cost of expansion, building, operating facilities, blah, blah, blah. As technology changes, we may make bats differently. Bats themselves may be made differently. Maybe they're no longer going to be made out of. Maybe we're going to obsolesce what it is we're making. Maybe they'll be made out of carbon fiber, or something like this. So, that would be an example of technology being an important factor in what we're trying to do and what we're trying to deliver. A behavior of competitors. Maybe somebody has found a way to do it faster, bigger, better, cheaper than what we can do. And so those are always the competitive forces we're dealing with. And then, of course, we have the availability of capital. And that's based on a lot of things. And I'm not going to teach the finance course here because I'm sure we've all had corporate finance and managerial finance and so forth. But at the end of the day, and if you hear my dog barking in the background, he hates the Amazon guy, the FedEx guy, and everything like this. So he's outside yelling and screaming about something. But in any event, so the availability of capital and the cost of capital. Sometimes we see firms like even Elon with what he's trying to do. And Elon is, trying to take several things public and for arguably good reason, because going public is a good, easy way of being able to raise capital. Uh, the argument is that, then you get owners of the firm. And if you're not the majority shareholder, as Elon is, but if you're not the majority shareholder, then there's a chance that companies, different companies, private equity companies can come in and basically gut the money out of the business, and the entity ultimately collapses. And this is what's happening with most of the fast food chains and so forth. So capital is obviously an important factor. Key decisions of capacity planning. Well, the amount of capacity needed. And again, where's that capacity cushion? Timing of changes, the need to maintain a balance between the system, what exists and what could exist, the extent of flexibility of facilities. At a point in time, we were looking at a concept called group technology. This was big at Eastman Kodak, and Eastman Kodak at the time looked at group technology and they said, you know what? We can't afford to do these total factory automation systems. But what we can do is, we can group parts that have to be manufactured. So if something is cylindrical and it's got a rather high length to diameter ratio, for example, a baseball bat. So you look at a baseball bat and it's compared to its length, which varies, I guess, between, I don't know what, 30 some odd inches and 40 inches or something. That's how long they typically are. But diameter wise, especially at the small end, but diameter wise, relative to the length, they're very small. So it's got a very high length to diameter ratio. Excuse me. So when we look at parts like that, we said, well, gee, what other kind of parts? It doesn't have to be the same size, but it's got to be something that, in terms of handling and machining and so forth, has that same kind of a range, a length to diameter ratio. So yeah, I could probably make a baseball bat in this group of machines just by making adjustments to tooling and dimensions and programming and all of this. But I bet I could make some, you know, copier shafts or maybe even drive shafts for cars. Why? Well, because same thing, a high length to diameter ratio. Another example would be for machining centers where you're not going to be turning something on a lathe, you're going to be machining it So maybe you have these big square blocks of different types of materials, and one is just a big square that you drill a whole bunch of holes in, and one is a big square that you mill out the center into some kind of a big cavity because something has to go inside of that. So the idea is, again, that when we design systems, they've got to be somewhat flexible. And one of the techniques to do that is something called group technology. Steps for capacity planning. Well, we did that with Betty's bats a little bit. Forecast future capacity, future needs. Evaluate the existing capacity. Well, then we would continue on to identify alternatives, look at the financials to see if all of this makes any sense, assess key qualitative issues, select one alternative and implement it. And then it's the feedback loop, monitor the results, and so on and so forth. So forecasting capacity requirements, we still talk, although it doesn't really apply that directly, but we still speak in terms of long-term versus short-term capacity. Long-term relates to overall level of capacity, such as facility size, trends, and cycles. Short-term relates to variations from seasonal, random, and irregular functions. So again, all of this stuff we kind of dressed a little bit when we were talking and forecasting, and it comes into play in different ways. Calculating processing, well, so you've got a textbook example here. Product number one, annual demand is 400 units, processing time, five per standard processing time per unit, 5 hours, and the aggregate processing time needed 2000, and so on and so forth. And this is what we did with Betty's batch. You look at the bottom and it says, well, this is based on working an 8-hour shift, 250 days per year, exactly what we did in the Betty's batch production sheet, and so forth. And then planning service capacity, well, need to be near the customers. Capacity and location are tied. The inability to store services means that we've just got to be efficient in how we use them and how we aggregate them. And then the degree of volatility of demand also is a key driver for what we look at doing. All right, so that's 14. I'm going to do one more slide and we'll call it a day. One of the things that we looked at when we were doing the leading up to the tropic sun example was the make buy option when we were looking at those slip rings, the Electro Poly or New World Electro or whatever we called it. And, we started to talk about the efficiencies of making or buying and what those costs are, with the end game being that we wanted to minimize cost. So, as much as possible, we wanted to make an optimal amount in-house and buy only what we had to. So, I'm going to leave off here and we will pick up this on Friday. This is all we're going to do for today. And so, let me just stop the share for a minute. And, since it's you and me, if you have any questions, just email me or whatever. Otherwise, I'll be back here and we'll finish the rest of this on Friday.
See you Friday. Have a good one, Professor.
You do the same. Have a good one.